So yeah, so that's work that has been done mostly by Valentin and Rob. Just in case you're not familiar with that, that's the map of where we have radars in the operational network. So every time you have a black diamond, it's a Doppler radar, which means that it's not only measuring the intensity of precipitation, it's also measuring how it moves, which is the Doppler velocity. And the little, it's about radar wheel. So that's Wheel's operational radar network. Because he's been working at the bureau before getting a real job. Yeah, and the purple circles are where radars are being converted to Doppler. So we are going to have a very good coverage of 33 out of 62 Doppler radars in the network in the next 2 or 3 years. So that's interesting because there are critical areas where you need that information if you want to detect mesocyclones or if you want to detect very severe weather, like in Queensland and around Sydney. You really need that sort of information, and many radars were very old radars that are being upgraded, so we're very excited about that. So that's the list of radars that are going to be upgraded. So that's the situation. So why, I guess you're not familiar with that, so why do we need calibrated radars? I've tried to talk about 3 things here. The main thing is if you're a forecaster and you live in WA, for instance, you're used to your radars, and everybody knows that they're not calibrated, so they will adjust what they think is severe weather, and then they move to Sydney, where they have a completely different strategy, where they try to really get the radar well calibrated, and then all of a sudden everything appears either very mild or very, very severe weather, and they will freak out for something that's not really important. So when you have an operational network like that, you really need to get something that is the same standard. And anyway, if you want them to use those measurements quantitatively, I have this example for rainfall. The easiest way to convert the reflectivity measurement we make with radars to a rainfall rate at ground, which is what people are interested in, you have this conversion. So it can be rain rate equal 1 factor times the reflectivity power something. This is a relationship from the 50s that we still use, but it's very variable over Australia. And so if you take now a reflectivity of 40 dBz, you get a rain rate of 12 millimeter per hour. If you take 45 dBz, all of a sudden there's a factor 2. So then what you do is at the basin scale, for instance, you're accumulating that over the basin. And if you have a factor 2, it's twice as much water in the basin. So you really have to get a proper value for your reflectivity if you want to provide information, quantitative information. The other example I wanted to mention here is a plot from Rob. Rob has been working a lot on hail, and one of the things we use is this mesh, which means maximum expected size of hail. So it's really the size of the hailstone that are going to fall on your head. So it's kind of an important thing to know. Am I going to get 3 centimeter hail or 6 centimeter hail on my head? That's an illustration for a very high-end case, which was the Brisbane hailstorm in 2014, which has over 1.2 or 1.3 billion dollar damage in the Brisbane area. Yes. Sorry?
My car got hit written off.
Yeah, well, I think you're not alone. Yeah, there's been a lot of that. And so a factor 2 in hail size, you can get easily, I think that was when you take 5 dBz as well?
Yeah, so I just took 5 dBz.
Yeah, so 5 dBz miscalibration would tell you that the maximum hail size you will get is 10 centimeters or 6 centimeters. And just to give you an idea, if you have 3.5 centimeter or 6 centimeter, that's your roof that is going to collapse or not, depending on the size, the type of your roof or anything. So you really need something that's accurate enough to know if your roof is going to collapse. And 1 centimeter can actually make a difference. So that's the 3 main motivations we have as a team to say, well, you really need to calibrate your radars properly. So we've been doing a lot of work on that, and we came up with 3 different techniques, which both have pros and cons, which I will describe very quickly, and maybe Valentin and Rob can go into more details in other talks if we have time. The first one is called the Relative Calibration Adjustment, or RCA. So that's a paper that Valentin published last year. So what it does, it's tracking changes in radar reflectivity very accurately. 0.5 dB, as you've seen, is quite accurate, but it's not an absolute calibration technique. So you can check how it changes with time, but you don't know what the baseline is. So you can be 5 dB off, but be very accurately tracking the value. And the way we do that, I will explain in the next slide, so I won't go into too much details. But the thing is that the changes that we observe in that time series can be due to different things. It can be due to calibration, so like your transmitter is dying or the receiver chain has a problem. But it can also be azimuth elevation issue. For instance, so what it does is that it measures, imagine you have a tower, you're hitting it, but then you have an elevation error and you're hitting it differently. The value of the reflectivity we get from that tower is going to be different. So if there's a difference in azimuth and elevation, it's also going to change the time series. So it's not just calibration, so that's one thing that's important to remember. The second one is using a satellite radar. So there's a dual frequency radar on the satellite called GPM. It's a NASA satellite. It's a NASA JAXA, so the Japanese Space Agency and US Space Agency. They've been working together on that. And so what we do is that we send them the coordinates of all the radars of that map that I showed you. And what they do is that every time there's a swath of the radar within 250 kilometers of any of our radars, they send us the data automatically, and then we process that with the technique that Rob has developed. So this one provides an absolute calibration because you're comparing two radars, and we know that the satellite radar has been very thoroughly calibrated. But because of many issues, you can have the storm that is moving, there can be time differences. So Rob has studied that very carefully, so there are different sources of errors. We think for each individual case, we have an accuracy of about 1.5 to 2 dB, which is, we want to be better than 1 dB. That's the target for us. So it can be better than 1 dB if we know that the calibration hasn't changed, and then we can average different points, different estimates along that time series. And that's why we want to combine the two techniques, because this one doesn't have the absolute calibration, but it's very accurately tracking, while the other one has estimates of the absolute calibration, but is not as accurate. So, you can't have everything. And then the third technique is a solar calibration technique. So what you're doing is that you're pointing at the sun. It's by accident, actually. We're not pointing specifically at the sun with operational radars, but we receive solar hits. And you can track both the azimuth elevation accuracy and the absolute calibration of only the receiver chain, so half of the radar. So again, it's not perfect. None of the three techniques is perfect. So, and the accuracy, we're not too sure about the accuracy of this technique. That's something we want to work more on. So just a little bit more detail to show you how it works. So this is a map of the first 10 kilometers of each radar. So for each radar of the operational network, we build a map like that, which is detecting permanent echoes. So that's trees, buildings. Sometimes we have 3 or 4 points, so we have to work with that. But for some areas like Melbourne, we have lots of ground clutter everywhere. So that's a beautiful spot for us. And that's the result of, so what we are tracking is it's a bit technical, it's the 95th percentile of the reflectivity of all those points. And this is very stable. It's been shown that it's not changing much. That's how we track a change in reflectivity. So we build that clutter map, then we calculate this 95th percentile of reflectivity, and that's the time series you see here. So that's individual 6-minute estimates. Then that's when you do an hourly average, and then the daily average. So you can see the scale here goes from 72 to 78, so it's well within 0.5 dB. So it's just to illustrate that we can really track that very carefully and very accurately. So from that technique, we've built an operational website which looks like that. So it's really internal because it's not very good looking. But for each we have more radars now because there's one requirement that we need to get the raw data, which we don't have for all the radars of the network. We have designed that 3-color map where when it's green, it means nothing has changed. And then we can detect changes in the daily value and changes in the weekly value, because what can happen is that you have a slight change, a very gradual change of the reflectivity, like we are losing power, but gradually. You won't be able to detect that from a big change in one day to the next. So you have to try to track long-term trends. So that's what we do with that tool. And that's just one example. Broadmeadows is the backup radar of Melbourne. So you see that kind of thing that we detect. So 63 goes to 64.5. So you clearly see step changes like that with that technique. So we're pretty happy with the outputs. That's the illustration of the GPM technique. So that's the one that does absolute calibration, but not super accurately for each individual points. So that's the kind of track you get from the radar, from the satellite mission. And every time there's a hit, as I said, you're looking to build collocated samples. So you have to do some averaging. And really, it's very simple. It's just you're just comparing two radars, but really the devil is in the details with this technique because there's time difference. You allow up to 6 minute difference, so in 6 minutes the storm can move by a lot. So you will have to assume that it's still collocated, which is a bit. But statistically, we found that it was not changing that much. But maybe for each individual point, it will introduce some variability. How much of this grid is filled in if you have just a little storm in that area? There's a few things here that can explain why we have 1.5 to 2 dB accuracy. And again, with that technique, we build this operational website. Looks a bit better. Still a bit. I think we can do better. And for each radar here, you have one dot, which tells you if the radar is calibrated to better than 1 dB, better than 2 dB, better than 4, better than 6, and so on. So we've got our black sheep, as we call them, around Australia. And so it's a difficult challenge internally at the Bureau for them to accept that the radar is 10 dB out of the completely miscalibrated. So we are still fighting to try to get some operational things happening when we tell them, well, this radar is completely out, you have to do something about it. What's interesting as well is this region where we are in Darwin. We know the engineer very well. I've worked with him a lot for a very long time. And they're all exactly calibrated in the same way, but they're all off by 5 dB. And we've discovered that the reason is that they use some material to actually measure the gains and losses inside the radar, but this is not calibrated. So the tool they're using to do the measurements is not calibrated. So from one region to another, you can have differences, but so he's doing a really good job. It's not the problem. The problem is that the tools that he's using to actually work out the calibration is wrong. So now finally they've agreed that they're going to send all these materials to the head office and calibrate those tools before they can calibrate the radar. So that was one lesson. So that's what you get for each individual hit. You have the distribution of reflectivity from the ground radar in blue and from GPM in orange, and that's the distribution of the difference. So you see it's a very nice peak, and so you see for this one that's the value we get, and then from this you can build time series with the standard deviation as well, which is how wide this distribution is, and so we can track that. And again, I will talk about it later, but if you have the tracking of the other technique, you can take time 0, time 1, and average all those points to get a much better, which is this red dashed line here. But see, the third technique is the solar technique. Basically, you're pointing at the sun. That's the azimuth and elevation. So you can scan. This morning we did that much more accurate scanning of the sun. You got in color here. You have the power, and here you have the difference in the expected location of the sun, because you know where it's supposed to be, and where the radar is telling you that it is. So that gives you how much mispointing we are doing with the radar. And the other plot is the expected solar power that we receive against the reflectivity that we measure, which gives us some measurements as well. So we've applied that in the previous leg. Valentin has worked on that and applied it to our weather radar upstairs, and that's what he found. So at the moment we think it's fairly mispointing by 2 degrees in elevation, which is actually a lot, and 1 degree too much clockwise. So we are going to work on that actually this afternoon, and late afternoon we are going to do some very accurate scanning with the weather radar of the sun to confirm those numbers. All right, then that's just to illustrate the interest of combining those techniques. So in that case, it's using the tracking technique plus the solar technique. That's one way to tell if it's calibration or mispointing, as I was explaining. We saw that on the Sydney radar. On the left here, you see this big decrease by 4 dB, 3.5 dB in the Sydney radar. And so we were wondering, well, is that because something happened to the pointing angles? And you actually can see that at exactly the same time here, this is changing by, so we are pointing at the ground clutter in a different way because of this azimuth. So in that case, it's not a change in calibration. So we are able to do that. And our next step is to do that operationally now. It's just research mode at the moment, but we want to do that operationally. And that's what this slide is about, just to explain what we want to do. We want to combine 2 by 2 or 3 by the 3 techniques together to work out exactly what's wrong with the radars or what's right. It's be positive, something can be right with radars. And so I just want to finish to show you what sort of instrumentation we have for that voyage. So of course the main thing we're interested in here is the dual pole seabed Doppler radar. So you can't visit the golf ball, but you can have a look from the Monkey Island if you stay within the boundaries that are allowed. There's a disdrometer and micro rain radar. So when we left port, many people were standing on the 5th floor like that. So the other instrument is not there because it was not there when I took the picture. But it's measuring the drop size distribution, which we want to use for our calibration work as well. And the micro rain radar is a vertically pointing radar at the same frequency as the satellite radar. So we're going to do some comparisons as well. And there's a container on the foredeck that has the cloud radar and LiDAR. Those are two of my instruments. And then there's another disdrometer on the mast as well. So everything to measure rainfall, precipitation, and clouds. So that's what we will be collecting. I think that's all I wanted to say. Yeah.